Hello all, this is David Ong and I'm about to execute my simulator software to show you a real-time simulation of the Arcjet, the way it was intended to operate. So this is a picture of the Arcjet and it's firing its rocket. I'm just using a picture of the Arcjet instead of a proper model for now. In the future, this software will have the ability to upload full CAD models instead of just having a picture as a placeholder. Now what you're looking at is the Earth, a 2D representation of the Earth. These are longitude, so you're looking from the North Pole, right? And you can see the internals of the Earth, the core, the inner core, mantle, etc. This green line is our target altitude, also known as our target apogee, of 550 kilometers. The red line is what we call the Kármán line. It is 100 kilometers above the altitude, above the sea level of the Earth, and it marks the region of space, the transition from our atmosphere to space. So anything beyond this red line is considered space. Now this line over here, these two lines, the red line and the green line, is our trajectory. So if I was to switch off our engines right now, this aircraft will follow the trajectory, like a non-powered ballistic object. But we need to keep our rockets on. So our rockets are on, as you can see, and we're burning jet fuel and liquid oxygen. And as we do, we're gaining speed. Our speed is currently, where is it? 3.6 kilometers per second, and increasing slowly. Now with the atmospheric modeling in this simulator, I haven't got our coefficient of drag numbers yet. Well, actually I do, but I haven't input them into the software yet. So at the moment we're using a very basic modeling of aerodynamics, because the purpose of this simulation is just to prove that we have the energy to get into space and back. We're focusing on delta V, not on aerodynamics yet. We'll do aerodynamics, we'll combine the aerodynamic properties into the software once I input those C of D numbers. Okay, so our trajectory, we need to get them up to the green line, and that's not counted because that's after a deflection from the atmosphere. When the aircraft falls back into the atmosphere, it'll bounce, and that's why this trajectory shows a bounce. And the reason why we have two trajectories, a green line and a red line, is because the green line is our orbital trajectory, whereas our red line is our trajectory relative to the rotating Earth, the rotating ground of the Earth. So the Earth rotates. That's why this, if you look at, where do I put this? That's why this red line is constantly moving away from the green line, right? We're talking about these longitudes here, and that's because the Earth is rotating in real time in this model. This is an ultra-realistic model of the Earth. Now let me see what's going on. So it looks like we're getting there. I have to wait for this green trajectory to touch this green line, this green circular line. Once it does that, I'll switch off my engines. Oh, wait a minute, we're out of fuel. What's going on here? That's not good. What's going on? So I'm accelerating time now, so that we don't have to wait 40 minutes for the flight to complete. Now, as you can see, the aircraft has no problem achieving the delta V that it needs, but we need to implement those upgrade the aerodynamic model to confirm that we can actually escape the atmosphere with enough fuel left to do what we're doing now. And with the basic modeling of the atmosphere, we don't have, we're like 75% there. We need to confirm that this aircraft is aerodynamic enough to not waste too much fuel doing what it's doing now. Now, if you imagine you're on the North Pole looking down on the Earth, you will realize that the aircraft is actually moving from west, from west to east. It's going eastward, right? And that's very important. The aircraft will not work going the opposite way. It will not work launching westward. It has to go eastward. And the reason for that is because it needs the rotation of the Earth to give it the extra delta V or velocity boost to get into orbit. Which is fine, because we're talking about destinations that are on the opposite side of the planet. So it shouldn't matter which direction you move in, because it's going to take equal amount of time anyway. And as you can see, this square grid is now slightly tilted. That shows that the Earth has rotated since takeoff. So our target really should be here, where my mouse arrow is. So we're going to end up entering back into the atmosphere about 10-20 degrees away from our destination, which is fine, because once the aircraft reaches the atmosphere, as it's doing now, it's going to revert back to its jet engines. So obviously we'll have some reserve fuel for atmospheric flight on the way down, or it can glide. So a reminder, the atmospheric modeling is not very realistic at the moment, and it needs to be upgraded. But that's going to be on the next upgrade on my software. These circular explosions are actually a simulation of the speed of sound, so that you can appreciate how fast the aircraft is going in comparison to Mach 1. The atmosphere is modeled using standard atmosphere. So you can look it up on Google, what standard atmosphere is. So as you can see, the aircraft has bounced off the atmosphere and still have enough velocity to actually go way beyond its target, which is over there. So in terms of energy, we have no problem, but we have to confirm that the aircraft is indeed sleek and aerodynamic enough to not burn more than the fuel that we've burned, to get to where we are now.